We are asked the force on charge Q1 from these other forces. All right, so we've got three charges. Q1 is 1 microcoulomb, charge 2 is negative 2 microcoulombs, and charge 3 is 3 microcoulombs. And situated as shown, and we want to know the force, the total force that Q1 feels. All right, so what governs this? When we have charges and we need to find a force, we need Coulomb's law. All right. Coulomb's law says force from 1 to 2 is K, Coulomb's constant, Q1, Q2 over R12 squared, and then we have a little R12 hat here. So the way that we like to do these problems is to look at the forces between two sets of charges. So this Coulomb's law gives us the force between two different charges, 1 and 2, right? It doesn't do 3, right? So what we do is 2 at a time and then add up the results on the charge we're talking about. So we're trying to find the force on charge 1. So first we're going to find out what 2 does to 1 from Coulomb's law, and then we're going to find out what 3 does to 1 from Coulomb's law, and then we're going to add those together as vectors. Remember, force is a vector, right? So it has magnitude and direction. It has x and y components, however you want to think about it, but it has multiple parts, okay? This little r hat means a unit vector, and from the direction, in the direction from 1 to 2. So for this one, it would be a little vector 1 unit long from 1 to 2. Most of the time, what we're going to just do with this equation is just calculate the magnitude of the force first, and then use the diagram to get the direction. All right, so let's just go ahead and do that. And so let's kind of have some steps here. So step 1 is draw. Okay, let's say draw and data. Draw the diagram, put data on there. We've got a pretty good diagram here. We might do a little bit more here in a minute. 2 is find magnitude of forces. All right, so each force we're going to be looking for, find its magnitude from Coulomb's law. And 3, find vectors. Vector forces, force vectors. And then 4, add them up. All right, so we go use what's called superposition. We find each individual one and we can add them up together. All right, to get the total. So let's just kind of look at, well, that's right. So F total on force on charge 1 is going to be the force. These subscripts mean from 1 to 2. So what 1 does to 2, right? So what we want is what 2 does to 1 and what 3 does to 1, right? And their forces. And so we have to add up the forces, calculate what force 2 does to 1, and then what force 3 does to 1, and then add them as vectors. So let's just look at the diagram just a little bit more. We don't need to do this now. We could do this when we're finding the force vectors, but let's just draw a little bit so we recall what we're doing here. And so we have two charges, Q1 and Q2, that we're considering first. One is positive, one is negative. So when we have charges, law of charges says opposites attract. So we're going to think about Q being held here, and what's it going to do to 1? Is 1 going to be, remember, force is a push or a pull. Is 1 going to be pulled or pushed? In this case, it's going to be pulled. And so we can draw the force like this, right? Because Q1 is going to feel a pull. I think of this as an arrow, something pulling it. Q2, right? The charge of Q2 is pulling Q1 towards itself. So this would be force on that 2 does from 2 to 1. Force that 2 does on 1. So when we're talking about F21, is this force here. It's a little hard to see maybe. All right. And then how about, so while we're at it, let's do 1 and 3. All right, so charge 3 is positive, charge 2 is charge 1 is positive, and so we want the force that 3 does on 1. The force always is in a line, straight line, make a straight line between the charges we're talking about, as we did here, and the force is always on that line somewhere. It's either going towards or away. In this case, like charges, both positive, are going to repel. Again, think of Q3 as being held. what's it going to do to Q1? It's going to push it, make it go this way, right? So Q3 size-wise is a little bigger, but it's a little further away. So this, I don't know, the size of the vector might be something like this. I'm just guessing pretty much, but this would be force from 3 to 1 as a vector. All right, it has a length and then has a direction. All right, so we're going to add those two together as vectors. Remember when you add vectors, kind of makes a parallelogram kind of thing here. And so the resultant, or you can think of taking this one and putting it tip to tail here. Either way, but the resultant should be something like this. So this is F1 total, right? It's the total force that F1 is going to feel. So if you could have these held still and let that one go, it would move off in this direction, right? It would have an acceleration, go in that direction. Okay, so we got our drawing and our diagram and our data pretty well noted. All right, so let's say we're done with 1. Let's look at part 2, find the magnitudes of the forces. All right, so we want F21, just magnitude-wise. And so when we're doing that, we're just going to take, this is a unit vector that's just 1 unit long. It's telling direction, so we're just going to ignore that and just take the rest of it. So it's going to be K, Q1, Q2 over R21 squared. R21 is like a radius, but it's really just the distance between the charges, right? So R21 is the distance between 2 and 1. And again, since we're doing magnitudes, we'll keep everything positive. So Q being negative doesn't matter. We'll just take positive because we're doing magnitude. We're doing the length, right? The distance. Okay, so let's put in some numbers here. K is Coulomb's constant, right? K is 8.9876. Let's see, Newton meter squared per Coulomb squared. So that should be on your equation sheet somewhere. Coulomb's constant. We're going to use it quite a bit in this chapter. So 8.9876. Whoops, I forgot my times 10 to the 9th. Times 10 to the 9th. All right, and let's just put units on here for the first calculation just to make sure things work out. And then we're going to have Q1. Q1 in size is 5 micro. I'm sorry, not 5, 1 micro. What is micro? 10 to the negative 6 coulombs. And everything in its nice standard units here. And then Q2, like I said, we're going to ignore the sign since we're doing magnitudes. 2 times 10 to the negative 6 coulombs. All right, so that's K, Q1, Q2. We're going to divide that by R21 squared. R21, like I said, is the distance between 1 and 2, 2 to 1. 5 centimeters, want standard units, so we got to use meters and squared. All right, so checking the units. So this is still F21, continuing down here. So checking the units, in the bottom of the fraction, we're going to have meters, but it's squared. It's inside the parentheses, so it's going to be meters squared, so that's going to cancel with that meter squared. All right, so that's good. Up here on the top, we have coulombs times coulombs, but then in the bottom of the top fraction, we're going to have coulombs squared, so we can those will cancel out as well, and so we're going to be left with newtons, and newtons is what force, the unit of force, so this is all good. All right, so let's punch that into our calculator. 8.9876 E9 times 1 E negative 6 times 2 E negative 6. Let's just put that in parentheses for safekeeping. Divided by, let's put that in parentheses for safekeeping, 0.05. Close parentheses and square the thing. All right, so hit enter, and just, my calculator is quite nice. Hopefully yours is too. You can see how it interpreted the equation. Looks like it put everything in the right place, and then we've got an answer there. So the force is 7.19. Let's go with 4 sig figs for a minute, but 7.190 newtons. And that is the force from 2 to 1. Magnitude only. All right, no little arrow thing on top because it doesn't have a direction. We just know how big it is. It's the length of this little vector here. All right, let's go ahead and get the magnitude of the other one. So let's get F31 using Coulomb again, same formula, KQ1, but now it's Q3 over R31 squared. K, still the same thing. And then Q1, still the same thing. And Q3 is now 3 microcoulomb, so 3 times 10 to the negative 6. Everything is still in standard units like we were doing before. The length here is given as 6.5 centimeters, so 0.065 meters squared. All right, so let's go ahead and get F31 then. All right, so K times Q1 times Q2 and all that divided by 0.065 squared. Looks good, so we get 6.382 newtons. Okay, so let's kind of box or underline anyway. Let's just put a box around them just as a kind of keep track of them a little bit here. All right, and so we got our vector magnitudes of our vectors. Now we want them to be forces, because we have to be forces to add them together, because they're not going in the same direction. If they were exactly in a line with each other, right, they're all in this, had the same direction vector or negative sign of each other, we could just add or subtract, but they aren't. This one goes straight sideways, this one has an up and down component and a sideways component, so they cannot just add straight to each other. All right, so F21 as a vector, lengthwise it's 7.190 newtons, but what is the unit vector? What is the direction? Well, looking over here, we see that it's going straight in the x direction. What is the unit vector in the x direction? Remember, x gives us I hat. I hat is just a little vector 1 unit long going in the x direction, right? Y, we have j hat. Again, a little vector 1 unit long going in the y direction. And if we had a z, then we would have k hat. So we got x, y, z, I, j, k, right? Would be, let's say this is the dimension coming out, it would be 1 unit long. All right, so if we have something in the purely only x direction, then we will just multiply that by I hat to describe its direction, and then it will be newtons. So F21 as a vector then is just 7.190 I hat. Notice F31 though, it has some x direction part, call it F31x, I guess, going that way, and then we have a y part, F31y, that's coming down. All right, or we could do y going down this way, F31y coming down, and F31x going here. It's the same thing, right? This way to this way, or down here and then here, you get to the same point here. Actually, let's look at this one because we got the 40 degrees here. This tells us the line because that's the line between the two charges, and so this has to be on that same line. So let's put the 40 degrees in there. 40. And so we need to find the components, right, of F31, right? So F31, when we do components of a vector, hopefully remember from physics 1, but let's just do a quick review here. If you have a triangle like this, any kind of triangle, but let's just do triangle here. It's a right triangle, and you've got F31 magnitude wise, you got F31y is this side, and F31x is this side, right? And so how can we find, we know F31, and we know, I drew my triangle different, but similar triangle, flip it over here. The 40 degrees is here, or we could think about doing this bottom triangle because alternate interior angles, this is also 40. However you want to think about it. But how can we know F31, we know the 40, how can we get these pieces? Well, let's start with x. So how is x related? Remember cosine. What is the definition of cosine? cosine of 40 degrees is, cosine is adjacent over hypotenuse, right? So f31x over f31, right? So if we wanted to solve this for f31x, is f31 cosine 40, right? Similarly, sine 40 is f31y over f31. So f31y is f31 sine 40. Alrighty, and so when we're going to write f31, we're going to write f31 x part, take it times I hat, and then the f31 y part, 31 y part, take it times j hat to get f31 as a vector, right? And it'll be in newtons since everything else is in newtons. And so in our case then, f31 is, f31x is this, f31 cosine 40, we have f31 here, so it's going to be 6.382 cosine 40 times I hat plus 6.382 sine 40 j hat newtons. So let's put those numbers in. 6.382 times cosine of 40, so 4.889 I hat plus 6.382 times sine of 40, 4.102 j hat newtons. All right, so we got our two vectors now, our two pieces. If we had more charges, we would have more forces. We could just keep finding the forces, and then in the end, we're just going to add up all the forces from all the things that are acting on our charge we're interested in. Okay, so we got force 2-1 and we got force 3-1 as vectors, so we can add them up if we can remember what they are. So F21, 7.190 I hat newtons. F31, 4.889 I hat plus, I just realized we did something wrong. 4.102 j hat. What did I do wrong? Alright, so we found fx and fy, f31x and f31y. Size-wise, they're 4 and 4. But looking over here, if we're going to make them vectors, they got to be with respect to the x and y coordinates here. And so f31x is here, either whichever way you want to do the triangle, but it's backwards x, right? It's going that way to get to the tip, from the tail to the tip. And similarly, y is going down. Okay, so we're going down and to the left, so both of those are negative in terms of x and y. And so I should have put a negative I direction and a negative j direction on this guy. Alright, so we use the triangles to get the length of the sides, but then we need to be careful. Look at the picture to see, okay, is that in a negative x direction or positive x direction? And if it's negative x, put a negative I hat. If it's down, negative y, put a negative j hat. Because remember, these are just little unit vectors that tell the direction. All right, let's put our minus signs in here so we get the answer right. Okay, so F1 total is a vector, and it's these two added together. So it's going to be, I guess I'll rewrite it, F21 plus F31 as vectors. And so it's 7.190 I hat is F21, and then it's negative 4.889 I hat minus 4.102 j hat. All right, so all this is F31. And so when you're doing vectors or any kind of algebra, you can only add like terms, right? So the only things that with I hat can be added to other I hats, and J hats can add to other J hats. So we only have one J hat, but we have two I hats, and so F1 total. The first term, we're going to add those two together, and actually wants to subtract. So 1.109190 minus 4.889. Okay, 2.301. I hat, that's all the I hats we got, those two together. J hats, there's only one, so we'll just bring it on over. There can't add to anything else. There's no other terms for it to combine with. Still, all the pieces are newtons. And so there we have it. So there's our F1 total. Probably for significant figures wise, I just say keep 3. So we'll have 2.30 I hat minus 4.10 J hat newtons. So that would be our force, our total force as a vector. If I want the magnitude of the force, magnitude of total force, then remember this is our total force is here. Did I do a very good job? Let's see. 2 in the x direction, positive, and negative 4 in the y direction. I didn't do a good job because it's supposed to be going positive x. So x is supposed to be this side of, anyway, positive x and down y. So my drawing didn't work out very well, but we're trying to get this vector. Didn't agree very well because this one actually is more like this, right? 2 over, if we got our coordinates, 2 over and 4 down. So this is really what F total looks like. Okay, so 3, well, so let's go ahead and see. So this is the 2.30, and this side is the negative 4.1 side. So how do we get the magnitude would be the length of this vector. How do we get the magnitude of it? Well, remember it's a right triangle where we put this 2.30 up here. So this side is 2.30, this side is 4.10. So c squared is just a squared plus b squared. So c is just the square root of a squared plus b squared. So in this case, F1 total, oops, I should have put my vector thing up here. F1 total, just the square root of F1 total x squared plus F1 total y squared. So F1 total is just the square root of 2.301 squared plus 4.102 squared. And technically it's negative 4.102 squared, but squaring it, you can lose a negative sign anyway. It's going to be a positive number. So we've got square root of 2.301 squared plus 4.102 squared. And so I went back to using 4 sig figs in my calculations and then just keep 3 in the end. So magnitude, so F1 total. When we write like this, it's just magnitude usually. We could also say the magnitude of F1 total, like absolute value signs, to be more clear. And my calculator says 4.70 newtons. Okay, so if it asks for the magnitude of the force, we could give something like that. Okay, excuse me. I think that's all that we were looking for there. So we will call that good.